So first, some of the identities that you need to know. So when I say identity, what do I mean? I can consider a case almost like a definition, so it's always going to be true. So first one, these are ones you do need to memorize. Sine theta is equal to 1 over cosecant theta. Who did not know that? Okay, we said sine was y over r, right? And cosecant was r over y. So that's basically what it's saying. Same idea. So that's all of these ones on the list are ones you need to memorize. So what would cosine be? 1 over secant. And tangent? Yeah. Do I need to write the ones for the cosecant, secant, and cotangent? Because no, they're just going to be identical to these ones. Cosecant would be what? 1 over sine. Secant. And cotangent. Yeah. So those ones, you still need to memorize them. I'm not going to bother writing them down. And notice that they are the same as these ones. Now a couple more of them. Tangent theta is sine theta over cosine theta. Now how am I going to justify that? When we look at the unit circle, how far was this part right here? X value, right? Whatever the x is. And what is x in terms of y and r? Or cosine. So we could say this part right here is cosine theta. Because it's our x value. X over r. So I could say it's x over r if I wanted. This part would be the sine theta equals y over r. What is terms of tangent? Opposite over adjacent. Sine over cosine. So cotangent would be, in terms of sine and cosine, cosine theta over sine theta. So those bottom two might be the first two new ones, but they are fairly straightforward. You memorize all of them so far. Next set is your Pythagorean identities. Now you need to memorize one of them, or all three, either way. However, if you have one of them, you can generate the other two. What is the Pythagorean theorem? A squared plus equals where C is your hypotenuse, right? So now if we consider this in the unit circle, what's the rate, or what's the hypotenuse in the unit circle? 1. How would I write the Pythagorean theorem for them? Yeah, and I like to put sine first, but it doesn't matter. Sine squared theta plus cosine squared theta equals 1. Have you seen this notation? Okay, so remember this means, the reason we put it there is to make sure it's clear that we're talking about the sine being squared, not the theta being squared. However, this by itself is meaningless, because sine has to be applied to something. So when you see this, this is the same as saying sine of theta squared. These two are equivalent. Now the other two Pythagorean identities. You don't have to memorize them if you have this one memorized. However, you can get to them from this. I'm going to divide everything here by cosine squared. What is sine squared divided by cosine squared? Tangent squared. What's cosine squared over cosine squared? Because tangent squared plus 1. And what is 1 over cosine squared? Secant squared. That is the second of the consecutive identities. All I did is take the original one and divide it by cosine theta, or cosine squared theta. How if I take the original and divide it by sine squared? What's sine squared divided by sine squared? 1. What's cosine squared divided by sine squared? And what's 1 divided by sine squared? So those, I'm going to just put that up here, you divide it by sine squared theta back from the original. You get this one. So if you can remember the first one, then just remember that you can divide by cosine squared to get one of the other one, divide by sine squared to get the other one. Or if you want, just memorize all three of them. Either way. Now, a few more of them to do. The co-function identities. Now, as you were graphing them, did you notice that sine and cosine were the same shape? Anybody notice that? They're the same shape, you're just shifting from each other. The rule for the shift is this. So if I had sine theta, and I graphed cosine of pi half minus theta, I get the exact same graph. And I could do the same thing with cosine theta is equal to sine of pi half minus theta. Now this also applies to all of the other ones. So tangent of theta would equal cotangent of pi halves minus theta, which means cotangent of theta, the tangent of pi halves minus theta. And same thing for secant and cosecant. So these are why they are called the cofunctions. Sine and cosine are the same function, just shifted off by pi halves. Tangent, cotangent, shifted the same function, shifted by pi half, and I guess I should say and vertically or and horizontally flipped because of the negative there. But and secant, cosecant, same idea. Now do you remember functions being odd and even? What's an example of an odd function? Y plus x is odd. What's another one? X to the third. What's another one that's not a polynomial? That's right. So what do you notice is true about the shapes if they are odd? Like if you look at the graph of them, what is true if you have odd functions? Okay. So if we're talking about odd functions, they have the shape where you could look at them upside down and be the same. Right? Does that sound familiar? Or we could say f of x is equal to negative f of x. Hold on, actually, negative f of negative x, is it? No, negative f of x. Yeah. So, back here, when we're dealing with this, some of these functions we dealt with were odd, some of them were even. So, which of the traits do you think are odd? Okay, tangent and cotangent are odd. So, odd functions. So, this is tangent of negative theta is equal to the negative tangent of theta. So, that, what else do you think is true in that form? So, cotangent is as well. What else? And over here, let's do some even functions. You know what even means? Okay? Or it is symmetrical across the y-axis. Which one is symmetrical across the y-axis?
Oh.
So remember, tangent does this, right? It is odd. Where does sine start? 0. So sine does this. Is this going to be odd or even or neither? Like if you look it upside down, is it going to look the same or different? Same, which means what is it? Odd. So over here, sine of negative theta is equal to negative sine of theta. What about cosine? What does cosine look like if you graph it? Where does it start? There. And what does it do from there? Is that symmetrical across the y-axis? Okay? So this point and this point symmetrical. This point, this point. So cosine is going to be an even function. So cosine of negative theta is equal to cosine of theta. Now there's going to be several different things you're going to be asked to do with these functions. First type, you're going to be given something like this. Cotangent of theta equals 5 over 7. Find the tangent of theta. 7 over 5. How do you get that? Yeah. Or a bit more complicated. Cosecant of alpha is equal to 7/3. Cotangent alpha equals 2 root 10 over 3. Find secant of alpha. Alpha is just like theta, it's just an angle. Which identity involves cosecant, cotangent, and secant? Or is there any? Okay, and what does it say? Okay, is that going to help us in this case? Okay. Okay. Which one of the second identities includes secant? Okay. Okay. How do I change this into tangent? So if you say tangent squared theta, or tangent of theta, or tangent alpha is equal to what? 3 over 2 square root 10. Now, I'm not going to have to simplify it because that's not my final answer.
Oh.
Now, can I use this to get secant?
Yeah.
Okay? So, I'll get in here. What am I going to get? What is this squared? Okay, what's the top? Squared. 9. What's 2 squared? What's root 10 squared? So what? Yeah. 40 plus 1 equals secant squared theta. Where's 49 over 40 coming from? Oh, from these two added together? Okay. So 49 over 40 equals secant squared theta. So secant theta equals 7 over 2 square root 10. That's what we started with, is 2 root 10.
Wait, how did you make that?
Okay, square root both sides.
Oh, right.
Now something we need to keep track of. Which quadrant do we have to be in? Because we didn't actually use this, right? In any of this stuff down here. However, this tells us what quadrant we're in. Why? Well, which quadrant is cosecant positive in? Okay, 1 and 2, so we know it's up here. Now, which quadrants are cotangent positive in? 1 and 3. So if you didn't have this part, you just have this, we want to know which one of these we were on. Which would mean that our answer here, if it was down here, would have to be a negative answer, right? However, if we know cosecant is positive, what does that force us to have? Positive, because we know we have to be in the first quadrant. So how would we finish this? But how would we finish it? Get rid of the root 10 off the bottom. Okay. Now, does that reasoning make sense? Okay. So sometimes, on some of these, they will give you an answer like this that doesn't actually affect the number of the answer, other than telling us where we're at, whether positive or negative. So it's important that you realize where is sine and cosine positive and negative, and tangent positive and negative. So if this was, for example, negative 5 7, or if this one was negative 7/3, then yes, we know we would have to be in third quadrant, which would mean we know our answer has to be a negative answer. Now, the more fun type of problems you're going to be facing are ones that are simplified. Which are something like this: cotangent x minus cosine cubed x times cosecant x. And we need to simplify this. Now, this is what our proofs are going to be based on, this type of idea of being able to simplify this, of seeing how we can simplify it. And sometimes you can't really see anything, and you just start off with trying stuff. So, anybody see anything they want to try? Yeah. Okay. So that is one of the strategies that is often helpful, is change everything to sines and cosines.
Change the
Yeah.
So let's leave this for now. Just hang with me. So cotangent x goes cosecant or cosine squared x times 1 over sine x. Okay. Anybody unclear as to how we did that?
We have to put sine x over all, or under all of it.
Nope, because no, it's only this one that's being multiplied by that. So no, I can also, so with these, you will definitely need to be showing steps. Don't just tell me what the simplified version is. Unless it's a simple one, like if you had 1 over sine, and you're told to simplify it, that's like a one-step then. So these ones, you're gonna want to need to show your steps. So cotangent x minus, I'm going to separate this into cosine squared x times cosine x over sine x. So notice this has 3 cosines, right? If I pull one of them out and put it over here, I still have my 3 cosines multiplied together. What is cosine over sine going to be? Cotangent. a second one of the big hints to do. So first one, change stuff to sine to cosine. Oftentimes that's helpful to do, and in a problem if you get stuck. Factor. Anything here we can factor. Is there anything common in both parts? So I'm going to factor out cotangent x. What's left over here if I factor out cotangent? 1. What's left over in the second part? Okay, 1 over sine became, I made it change to cosine over sine. Because I took the cosine out here and shared it. And then cosine over sine became cotangent. Okay, I factored it out. Remember, what do you do when you have, say, 3x plus 6? If you factor out 3, what happens? 3x plus 2. That 3 represents a 3 times x and 3 times 2. Over here, the same thing, cotangent. When I factor out cotangent, same as cotangent times x, or cotangent x times 1, will bring us back cotangent. Cotangent x times cosine squared will get us back to this. Yeah, so another thing another hint is look for Pythagorean identities. When you ever see something squared, you're going to be looking for one of the Pythagorean identities. So which one of the Pythagorean identities is this? Okay. So notice we had sine squared theta plus cosine squared theta equals 1. How can I get 1 minus cosine squared from this? So I can say sine squared theta equals 1 minus cosine squared theta. Right? Yeah, you can switch stuff around, and it's still the Pythagorean identity. So this becomes cotangent x times sine squared x. And we're almost done. Let's change it back to cosine over sine. So probably we could have left it back anywhere, like throughout the whole problem. However, if I have cosine x over sine x times sine squared x, what's going to happen? Okay, sine is going to cancel with one of these, leaving us just cosine x, sine x. That would be the final answer. So what were 3 of the methods? 3 methods that I highlighted there. Okay, so one of them, look, there's actually more than that, but look for Pythagorean identity. Which is cosine squared theta, either that has cosine squared, sine squared theta, secant squared theta, etc. All those. So that's one of the things. That if you see a cosine squared, like when we started the problem, we had a cosine cubed. When I see that, I'm immediately thinking, I bet I can reduce that to cosine squared and get a Pythagorean identity. Now, I might not immediately see this how I can do it, but that's one of the key things to look for. Okay, what was another one we did? What? Okay, so change to sine and cosine. No, those aren't all. Remember, these steps are not all ones you always do. These are just ideas that sometimes will be helpful, sometimes not. A third one, factor. A fourth one, we get to talk about in that problem, common denominator. This means if we have fractional ones, most likely we're going to want to get a common denominator to combine them. And let's see, other ones that might be useful. I'm going to put in here specialized cases. And when I mean specialized cases, I mean if you see something that has this in it, you're guaranteed you're going to be using one of those. Now, it's not even a question. You're guaranteed. If you have a pi half minus theta, you're going to use one of those co-function ones. If you have a negative in here, you're guaranteed to use one of these ones. So when I say specialized, I mean ones that are have a very specific pattern to them. Now, typically, you're not going to use these ones unless you have that specific thing. Like these ones, negative theta. These ones, pi half minus theta. And let's see, I think I had a sixth one I wanted to add, and I'm not remembering what it was. Anyway, let's do another one of these. Maybe we'll see it in here. 1 minus cosine x over tangent x plus sine x over 1 plus cosine x. And the goal is simplifying this. Generally, like one like this is really, it's hard for me to decide. Now, there's lots of ways. What's one idea you come up with? So his idea separates these. Okay? And that would be something you can do. What's another thing you can do? Okay? Changing sines and cosines here. So another one would be flip and multiply by 1 over tangent up here. Okay? Okay? So sine squared times cotangent, and where have you seen that?
I think 1 minus cosine of x is sine.
1 minus cosine squared. However, no, we could multiply top and bottom by 1 plus cosine. Right? And that would generate the Trig identity. So that would be something we could look into. Or, no, we get a common denominator, combine the two into one fraction. So any of them are valid ideas. Now, my first instinct when I look at this problem would be get a single fraction. So combine and get a common denominator. Because most of the time if you have a single thing, then that makes multiplication and division easier to deal with. So what would I do if I was going to do that? And 1 plus cosine x. This side we have to multiply by tangent. Now, one thing you notice, that is going to give us the Pythagorean identity up here. And most of the time, if you see that, it does 2 of these steps. Most of the time, that's the correct step. If it does 2 things out of that list of 5, you're almost guaranteed you're doing the right thing. If it does 3 out of the 5, I don't know if there's ever been a step that does 3 out of 5 with it being incorrect. So up here, I'm going to get 1 minus cosine squared x. Here, I'm not going to combine them yet because I don't know what's going to happen. Tangent x, 1 plus cosine x. And together, since I'm going to have that now, I'm going to have plus sine x tangent x. So now what? Okay, so changing this using the Pythagorean identity, get sine squared x plus sine x tangent x over tangent x 1 plus cosine x. Okay? So it's just changing sine over cosine. And that will give us a sine squared here. So you have sine squared x plus sine squared x times secant x over tangent x 1 plus cosine x. Anybody get stuck on that step? Okay, so I have sine x times sine x over cosine x. That's what this is, right? And this gives me the sine squared, and that leaves me with 1 over cosine. Okay, then what? Okay, what? Sine over cosine? Okay, so sine x over cosine x. Then what? Okay, distribute it. So I'm going to have sine, I'm going to factor out the sine squared because it bugs me in both parts. Have sine squared x plus, or times 1 plus secant x. I'm just factoring sine squared out of that. On the bottom, I'm going to have, I'm going to leave the sine out because I think I want to cancel with that. However, I'm going to multiply the 1 over cosine in. What's 1 over cosine times cosine? 1. Anybody stuck on that step? Or unclear what we did? What I did here is I took this part, we did 1 over cosine, multiplied that into both parts here. Yeah. It might seem strange to do that, and it could, and you might not see it. You might multiply this back out, but then you'll notice that there is a sign here that we can cancel. What's the answer with sine squared over sine? Okay? What is 1 over cosine? This part is just a secant x. 1 plus secant over 1 plus secant, cancel. There's my answer. Now, just because you can't see that does not mean you're going to get it wrong. There are tons of ways to do each one of these problems. So, there might be 30, 40 ways that are all correct. And you can, assuming you did all correct operations, you're going to get to sine x eventually. Now, I'll give you a representation of what I mean. Back when I was in just geometry class in college, one of the tests involved doing a proof, and it took me about 40, 45 steps to do it. But I got the correct answer. And I got full credit. The teacher, when we were looking at the test, did it in, I think, 9 steps. So if you do it efficiently, you can do it quickly. However, just because you're not doing it as efficiently as possible does not mean you're going to get the wrong answer.